Hi, everyone.
Good morning.
Good morning.
Hi.
Yeah, I'll be quiet. All right, man. Well, all right. Well, call me after 5.
Okay, so we're going to wait 1 more minute and then we're going to do our iClicker quiz.
Do we need a calculator or paper?
Nope, multiple choice, and it's not a calculation.
Dr. T, is it okay if I leave class like 10 minutes early? Because I have a meeting after, like, at 1 o'clock.
Yeah, sure. The most important stuff is probably going to be talked about at the end, so make sure to watch the recording, though.
I will.
Okay, so it's 11:02. You guys ready for your quiz? All right, let me share. You have 30 seconds. That tells you it's pretty easy. So share, there we go. So why is the mole important? This should be like a gimme, all right? 30 seconds. Okay, 5 seconds, put in an answer. All right, guys, what's the answer?
D.
Yes, it is D. It is all of the above. Please. Oh my goodness gracious. Come on, man. So yes, B is correct. Yeah, B is correct.
We can't see like the statistics.
Wait, what happened, Chloe?
We can't see like the statistics. Like when you the last couple times when you tried to share with us, it like flashes and it's not on your screen anymore.
Really?
Like I can't see what other people picked.
Okay, so
I don't know if it's me or the whole class, but
11 people picked the right one and 2 people picked B, as in boy, which is correct. I mean, that is a correct answer, but it's not the best correct answer. The best correct answer is D, as in dog, because it actually does all of those things, or is important because of all of those things. So that's disheartening that you guys didn't pick D. But anyway, okay, so that's that. Thank you for letting me know that. I didn't know that you guys couldn't see that. So today we are going to talk about oxidation states. Let me, hold on. Yeah, I'm not recording yet. Let me get to stop sharing. And any questions before we start? No. Okay.
Yes.
Oh, okay. What's your question?
I'm not able to find the session from yesterday's general chemistry session on Blackboard.
Yeah, it's not up yet.
Oh.
That's why. I'll get it up. I'll get it up. I'll do it. Sorry, but yeah, I'll get it up today. And I'll get this one up today too. So sometimes I forget. And yesterday, since we had the study session isn't up either. I was just busy. But anyway, so oxidation states, redox reactions. So do you guys know anything about this? Okay, because you should have read, right? Can anybody tell me anything about? Okay, go.
Okay, so an oxidation reduction reaction is like it's also called a redox reaction, and it happens when there's a change or transfer of electrons, and there's a reducing agent and an oxidizing agent, and the reducing agent is one that's gaining, no, the one that's losing electrons, or no, the one that's gaining electrons, because no,
It's the opposite.
the reducing agent is the one that's losing electrons, and the oxidizing agent is the one that's gaining electrons. And when something is reduced, it means it's getting more electrons because the
I think
number.
you've lost everybody, but you are
Okay.
absolutely right. All of that is true. So the first thing that she said was, or one of the first things that she said is really what the basis of a redox reaction is. So it is, how do you know if you have a redox? Is if you use these rules that we're going to talk about today and find that atoms or compounds from the left side of the reaction to the right side of the reaction either lose or gain electrons. So that is the definition of a redox. If there's a transfer of electrons somewhere, then that is a redox. Not all reactions are redox reactions. For example, a precipitation reaction. We just did that yesterday. So precipitation reactions do not transfer electrons. You can actually prove it to yourself after our class today, but they don't transfer electrons, so it's not considered a precipitation. I mean, it's not considered a redox reaction. Another one that doesn't transfer electrons is neutralization. And we haven't talked about that. We're going to talk about that on Wednesday. But a neutralization reaction, like an acid-base titration, that doesn't transfer any electrons. So that's not a redox. So that's how you know if it's a redox, if there's like a movement of electrons. Okay, so before we actually do those type of reactions, we got to figure out, okay, well, how do I know? How do I know if electrons have moved or transferred or whatever? So today we're going to start by going over those rules, because you've got to, when you get a reaction, you got to do these rules and figure out what everybody's oxidation state is, right? So when you do that, that'll tell you, oh, okay, we're transferring electrons, so this is a redox. Okay, does everybody understand that process? Okay, so that's what we're doing right now, is we're finding oxidation states, right? So that's just a number. It's a number that you assign to everybody's, to every atom inside a compound. But there's rules to that. So before we do it, we got to learn the rules. And if you guys read, you should have seen that there's, oh, why doesn't this start? There you go. Oh, that's weird. There's a bunch of rules, right? So you've got to know them all. But thankfully, I mean, really, for real, thankfully, you know most of these already. So don't try to read all of this. We'll go over it one by one. But these are almost similar to the stuff that you know already about charges for atoms. Like, how do you find the charge of an oxygen? It's -2. It's sort of the same answer, but for a different reason. Okay, so first of all, I have to stress, and I listen, right? If you guys usually don't pay attention, listen to this, because this is important that you understand. An oxidation state is not a charge. Okay, so I just said that about, oh, oxygen is -2, blah, blah, blah. Okay, but that is the charge of the ion when oxygen becomes an ion. Okay, we understand that. The oxidation state, it's going to look to you when we do these rules, it's going to look to you, oh, that looks like the charge. She's talking about the charge. No, oxidation state is not a charge. It's not the charge of an atom, okay? It is a theoretical state, okay? So it's in theory. It doesn't really happen. So can anybody, actually, before I tell you the definition, does anybody know what an oxidation state is?
Doesn't it tell you like how many, if it were to occur, doesn't it tell you which electrons would be going where, like halfway through the reaction?
So you're close. So it's a hypothetical state of an atom if it were to lose, if that atom, if that compound were to lose all of its electrons. right? So it makes pretend that every compound you encounter, every compound is ionic, which that's not true, right? Because you have molecular compounds. So molecular compounds are not ionic. But this state, this oxidation state, is a hypothetical state if the compound, if all the atoms in that compound were to be 100% ionic and lose all of its electrons. Okay? So that it's different. It's not real. It's not an actual charge. So you have to make sure you understand that. Does that make sense? And obviously, I didn't even realize it was written on the screen. It's a hypothetical charge if it was 100% ionic. But that's never exactly true for covalent compounds. Okay?
So would it always be positive then if it's losing electrons?
No, because you remember things are made up of metals and non-metals. So they have different, I'm going to say charges, but it's not charges. They have different signs. Okay? Because metals can never ever have a negative oxidation state. This sort of sounds like a charge, doesn't it? See, all these things that I'm saying are very similar to what a charge is, because I've told you metals can't have a negative charge. Well, it's kind of the same thing. Metals can't have a negative oxidation state, okay? So does that make sense or no? I mean, they're very good reducing agents, like metal. Well, you don't need to know that right now, but so they're not all positive because of how they're connected and because of the polarities of the particular elements. So it depends on how much that atom can actually lose, right? Hypothetically. It's not an actual losing, right? It's a hypothetical state. And another thing that might help you understand is that you'll see it's an average, right? It's an average of when you put all the atoms together in a compound, it's an average. If I was to lose all of the electrons, what is the average state, oxidation state that all these atoms will incur? Another way that you can kind of prove to yourself that it's not real is that you can get fractions, right? So you can't get a fraction of a charge. That doesn't happen, right? You have -1, -2, -3, or whatever it is. But when you do these oxidation states, sometimes you'll get an like a fraction. For example, if we do the oxidation state for that compound right there, what is that compound called? Anybody tell me?
Which one?
The one Fe3O4.
Iron tri-iron tetraoxide.
Huh? It's an ionic compound.
Iron oxide.
So,
right?
but it's a transition metal.
Oh, iron.
So anyway, we'll go from there. We'll forget about that. Let's not worry about nomenclature right now. But this is for you to find the oxidation states of every atom in that compound. You have to follow the rules that are down here, 1 through 7. All right. So I know you don't know what the rules are right now, but just listen to me. So oxygen usually has, and it's right here. It's, where is it? Number 3, right? So oxygen usually has an oxidation state of -2, right? So -2, you would put up here, right? So how many oxygens do you have? You have 4 of them, right? So each oxygen has a -2 oxidation state. So therefore, that means that that total side of the oxygen is -8, right? So you're going to equal it to 0. Does this remind you sort of how we used to do the charges? It's exactly the same process, right? So anyway, you equal it to 0 because there's no charge on the molecule. And then you have to find the oxidation state of iron. That's the question, right? So what is the oxidation state of iron? The way you would do that is, I don't know the oxidation state of iron because those are the ones that are kind of weird. I always know oxygen. I don't know iron. So I would put a 3x because there's 3 of them, okay? And then I would solve for x. If you solve for x, you see that you get 8/3, right? So it's not a charge because iron does not have a charge of 8/3. It has an average oxidation state of 8/3. If it were to be, if that whole compound were to be 100% ionic, it is not a charge. That's why it's that you can have fractions. I know you don't understand how to get those oxidation states, but do you understand what I'm trying to say about the difference between oxidation state and a charge?
Yes, ma'am.
Okay, so look at this last little bullet before we actually go over the rules. Do we include coefficients when finding oxidation states? What do you think? So for example, if I had a 2 here in front of that Fe3O4, would that make the oxidation states different?
Yes.
No.
No, because you have 2 Fe3O4s doesn't make the compound oxidation state different. Okay, it doesn't change how the average state of those compounds losing all of their electrons. You just have 2 of them. So it doesn't change anything. So coefficients, you know how coefficients are pretty important when you do molarity and precipitation. Yeah, but here it doesn't change anything because what you're talking about is just that compound. And regardless if you have 100 of them or if you have 1 of them, it's the same. It's the same oxidation state. Okay, so does that make sense, everyone? Hello?
Yes.
Okay.
Yes.
Okay, so there's 7 rules. They're really easy, you'll see. And we're gonna try them, we're gonna practice or whatever, but they're really easy because a lot of them seem very similar to the charges. Okay, so number 1 is a really important one. When you have a free element, so for example, if you're seeing a reaction magnesium solid, right? That's just by itself. So a free element that's uncombined has any free element. So if I have magnesium solid, lithium solid, I don't know, carbon by itself, if it's a free element and uncombined, it's gonna have an oxidation number of 0. You just have to remember these rules. So if I see a magnesium solid in a reaction, I would put a little 0 on top of it, okay? So that's rule number 1. In monoatomic ions, can someone give me an example of a monoatomic ion?
Chloride.
So chlorine, let's say if I had a reaction and the actual reaction had something like that, chlorine minus, like that's literally a product or a reactant. It was an ion, it's by itself, and it has a charge. So whenever you have something like this, the oxidation of the ion, the oxidation state of that monoatomic ion is whatever the charge is, right? So if you have a chlorine -1, well, guess what? The oxidation state is going to be -1. If you have magnesium +2, right? Let's say if you just had this, literally had that as a reactant or something. As a reactant in a reaction, then the oxidation state would be +2. All right, so that's what that means. Do you get that? Yeah, so now you've got 2 rules. If it's by itself, it's 0. If it's a monoatomic ion, it's whatever the charge is. Number 3, we kind of talked about. Oxygen this is the rule for oxygen. Oxygen is usually -2. Great. Because that's what the charge is when we ever talk about charges. So the oxidation state of oxygen is usually -2. The only time that it's not -2 is when it's in a peroxide. This is hydrogen peroxide. And I don't want you to worry about that because I am not going to give you a problem that has a peroxide. All right. So for you, all you got to worry about is this, which is easy. It's not really anything new. Oxygen is usually -2. Great. All right. Number 4. Number 4 is the hydrogen rule. So hydrogen is usually +1. Great. That's what it usually is anyways. So it's usually +1, except, and this is a big exception, except, look what it says, when it is bonded to a metal in a binary compound. So for example, right here, what is that called? Lithium hydride, right? Lithium hydride. So that is a compound that maybe you'll see in a reaction, and you have to remember, you have to assign numbers to everybody. So if I was to do that, I would say, okay, so lithium is a +1, okay? And then hydrogen would be a -1. What? That should flip your lid, right? Because hydrogen, it's not a charge. It's an oxidation state. So hydrogen is always +1, except when it's bonded to a metal in a binary, only a binary compound, which in that case, it'll take a negative charge. Why? Because metals cannot ever, ever, ever be negative, ever, ever, okay? So that is the rule for hydrogen. Everybody cool with that? Okay, number 5 is really easy because it's not even a new thing. Group 1A, so that first column, always +1. Great, that's what they always are anyways. Group, yeah, go ahead.
For the rule for number 4, so if it were like sodium hydride,
Yeah,
would be -1.
yep, sure would. Yep. So what was I saying? Oh yeah, group 1, number 5, group, so the first column, always +1, great. Second column, always +2, great. That's exactly like what we know for the charge. And fluorine is always -1. So that's a sort of an anomaly, and I'm gonna show you why, but fluorine isn't always -1. The oxidation state of fluorine is always -1, which is sort of not a new thing because that's what we used to call it when it has, well, that's what we used to say it was its charge. So you see that all of these are a lot of rules, but it's not really anything a lot new. The only thing that's really new is number 1. Okay, so I have to assign a 0 to something that's by itself. And the number 2, whenever the charge is, it's a monoatomic, it's whatever the charge is. Oxygen is usually -2, hydrogen is usually +1, group 1, group 2 are usually whatever they are as the charges. So nothing here is really new. Okay. Number 6 is also not new because we sort of did it when we were talking about ionic compounds and figuring out the charges of ionic compounds. So that little process that I did up here to find the oxidation state for Fe3O4, that's what they're talking about in number 6. So look, the sum of the oxidation numbers of all atoms in a molecule or in an ion is equal to the charge of the molecule or ion. So what that means is, you see why I put equal to 0? When I did that little math thing, I put it equal to 0. Why did I put it equal to 0?
It has no charge.
Because the whole compound has no charge. So for example, if I was to do if I wanted to find the oxidation states of everybody in nitrate, I would have to equal it to the charge of the molecule. So I would do equal to -1 because it has a -1 charge. So that's what that says. Sum of oxidation numbers of all the atoms in a molecule or ion is equal to whatever the charge or on the molecule or the ion. So let's just do it since we're talking about it. So NO3-, right? I want to find the oxidation states of everybody in there. To do this, you always will know all of them except one. So that's why it's a math problem. It's really easy. So what is the oxidation state of oxygen?
-2.
It's -2, but how many do you have?
3.
You have 3 of them. So 3 times -2 is what? -6. Right. And then you would plus, because you add them all together, plus an X, because you don't know nitrogen. It's not a charge. You don't know nitrogen, so you would put X, and then you would solve for X, which is exactly, if you remember, that's sort of the same thing I did up here with the Fe3O4. So X would equal what? +5. That's not a charge, because nitrogen does not equal +5 as a charge. This is an oxidation state, okay? So do you get it? Oh, and number 7, we don't have to worry about, by the way. So yeah, they're superoxide ions, which are actually quite common in nature. But anyway, I'm not gonna give you a question about superoxide ions, so you don't have to worry about that one. So really, all the stuff that you need to know is really easy, okay? So do you understand what we've gone over? Do you understand the rules? Because now we have to actually apply the rules to a redox reaction.
So for the oxidation of nitrate, that would mean that nitrogen loses 5 electrons?
That is the state, the average state of nitrogen. It doesn't lose 5 electrons, okay? You have to understand that. It's not losing 5 electrons. On average, if it was 100% ionic, that is the state that it would take.
Okay.
Yeah, it's a hypothetical.
What do you mean the state?
It's a hypothetical. So any other questions?
What do you mean the state when you're saying like the state it would take?
You have nitrogen and you have oxygen. They have different polarities, both of them. They have different electronegativities. So the amount of electrons, hypothetical electrons that they would give up, is what this is saying. But it doesn't happen. That's not true, right? Because when you talk about a charge, it's the actual physical electron that's moving from the atom. Here, you're taking into, and another thing, when you talk about a charge, is individual atoms, right? So this nitrogen individually gives up physically 3 electrons because it has an N3 minus 1 charge, right? N3 minus.
Is it like a prediction of what would happen, but it's never going to happen?
Right. And I don't know if it's yes, you can say it's a prediction. It's a prediction because it never, that does not happen. But how about, maybe this will, where I was going, will help you understand. Nitrogen physically, when it becomes an ion, gives up physically 3 electrons. That's what it does. When you're talking about oxidation states, you're talking about an average of all of the elements in that compound. As an average, how many electrons would all of those atoms lose together as a unit, right? Because everything is compared, it depends on who I'm attached to.
You said as an average?
As an average. Yes, it's an average hypothetical state. That's what it is. So on average, if I had 1 nitrogen and 3 oxygens around it, considering electronegativity and polarity, how many electrons would nitrogen on average hypothetically give up? It hypothetically would give up 5. But it doesn't do that.
Wait, nitrogen or nitrate would give up 5?
No, nitrogen, because look at X was equal to +5.
Oh.
And that was for
Okay.
nitrogen.
Okay.
Yeah. So hopefully, I mean, this helps us. The reason why this is important is because it helps us justify why things reduce or why things oxidize. That's the whole purpose of this. Okay, so it does not really happen. Nitrogen does not give up 5 electrons. Oxygen does not give up whatever, well, actually oxygen does give up -2, but for nitrogen and actually look, let me show you this. This was the next slide. So this is in your book, in your book. These are all the possible oxidation states. And another thing is, look at the hydrogen. I mean, the hydrogen never is a -1. It never takes on, it never takes on an electron. What? So that does not happen. It's hypothetical. So on average, if I'm connected, that hydrogen is connected to something that is way more powerful to lose an electron, it's gonna hypothetically take a negative charge. But it never does that. I hope that makes sense. Does that make sense?
A little.
Okay. The main thing is that these are not charges, okay? And you can't, when I ask you about redox, you can't go into your brain and say, oh, what's the charge? Thankfully, though, the rules that I have given you are similar. So if you don't remember, you can kind of fall back on that, but you have to understand, if I ask you to describe what an oxidation state, well, the first thing you should say is, well, it's not a charge. It's definitely not a charge, and it's hypothetical. It's a hypothetical thing. If all of the atoms involved in that compound would be 100% ionic, this is what would hypothetically happen, okay? And look at nitrogen, for example. Look at all of these different oxidation states. Look at chlorine, right? So chlorine has a -1 charge. Chlorine, when it becomes an ion, is always -1. It's so close to 8, right? Like it wants that that electron. But depending on who chlorine is connected to in a molecular compound, right? Because really it's about covalent compounds. In a molecular compound, depending on who chlorine is connected to, it will either lose or gain or whatever and have all of these different oxidation states. Any questions?
What?
No.
So it's going to be easy because all you got to do, you'll see, the process is remembering those oxidation rules, applying them to a redox reaction, and then just seeing who gets oxidized, who gets reduced. That is it. That is it. It's a lot of like pre-work to getting to understand it, but it's really easy. The process of a redox reaction problem is really, really easy. I will say that I said it before, you will always know all of them, like the rules for all of the atoms in a compound except one, right? So you can solve for that one if you need to. So one of the things that you should remember is you should never ever automatically guess what a chlorine is, right? Because look at how many different states chlorine has. And you should also, think about, look, nitrogen is also a big one. This guy, ruthenium, is also a big one, right? So you should never like say, oh yeah, no, nitrogen is plus minus 3. No, no, no. You got to always solve for that guy because you don't know. Okay, always remember these guys, the ones that are always. So column 1, column 2, oxygen for you guys is always going to be -2, right? So you don't have to worry about it. And then fluorine is always -1. So always remember those because that will help you solve for the other ones that you need. Okay?
So Nate, I have a question.
Yeah.
It's kind of like a visual question. So how come some of the, well, I don't want to call them charges, but like are red? Does that mean anything?
Yes, it does mean something. And I believe what that means, I don't remember what it means. I think it has to do with the, I don't want to tell you something wrong. I don't know. I don't remember what it means, but it does mean something. It might say, do you have the book? Because it might tell you in the legend in the book.
Yes, I have the book on me.
The most common ones. I think that's what it is.
Okay.
I think, but I could be wrong. Yeah.
I'll look later.
Sorry?
I'll look later.
Okay. You can, yeah, and I can look it up later. If you really want to know, I'll look it up later, but it does mean something.
I was just curious.
Okay, yeah. But it's not a big deal for what you guys need to know. You just need to solve for it and figure it out. So let's actually do some of them. Let's practice. Okay, so if I gave you Li2O, right? What is this called?
Lithium oxide.
Good job, lithium oxide. So I need to find the oxidation states of everybody in that compound. This one's easy because you should know both of them. So
Oxygen is -2, lithium is +1, but
Right.
there's 2 of them.
But each lithium is a +1.
Yeah.
So you put +1. You don't put +2.
You put
Okay.
it twice? No.
No, you don't write it twice. Each lithium, I mean, you can if that helps you, but that's not, I mean, each lithium is a +1. You just happen to have 2 of them. So what is oxygen?
-2.
-2. Exactly. Always for you guys, it's -2. That's it. You have found the oxidation states. That's what I mean by find the oxidation states. Okay? So, yeah, Taryn, did you have a question? No? Okay. So, what's the next one called? And
Nitric acid.
This.
Nitric acid.
Good job. So that's nitric acid. So what are the oxidation states of everybody here?
+1 for the hydrogen. -2 for the 3 oxygen. And then nitrogen we have to find, right?
Yes. So nitrogen we have to solve for. So what do I put it equal to? We have to set up a math problem.
0.
Okay, yes. We have to put it equal to 0 because there's no charge on nitric acid. So to set this up, how would I set it up? Tell me what I would write.
X +1 -2 = 0.
X +1 -2 = 0. No, no, no. So let's go in order of the atoms, right? So how many oxygens do I have?
Oh,
So what is the total number of stuff happening there? -6. Each oxygen is -2, but I have 3 of them. So that means there's a -6 plus X, that's for the nitrogen, plus 1. So if you solve for X, what is this? +5.
-5.
Right, so that is and if you notice, it's the same oxidation state than when I did before, you remember? For nitrate, it was also +5. So it just happens to be, it's the same number. Okay, so that's how you do it. You set it up like a math problem. Okay, so what is this guy? What is this ion called?
Permanganate.
Permanganate. Okay, what do I set? I want to know everybody, but I don't, which one's the one that we're going to solve for because we don't know?
Manganese.
Manganese. So what do I put it equal to?
-1.
Okay, so we put it -1, equal to -1. Then what do I do?
There's 4 -2 charges, so for the equation you put -8.
Plus
X.
X. Oh, sorry, plus X. So what is the oxidation state of manganese?
7.
+7. Does everybody understand that besides whoever's talking?
Yes.
Attorney, I
Yes.
have a question.
Go ahead.
So where would the -6 come from?
Are you talking
No.
about nitric acid?
Yes.
You have 3 oxygens. Each oxygen has a -2 oxidation state. So 3 times -2 is -6.
Okay.
Okay?
Yep.
Okay. So Austin, can you help me do this last one then?
All right.
What do you equal it to?
Would you equal it to 0?
No. Why did we equal nitric acid to 0? Why did we equal permanganate to -1?
Oh, because of the
charge.
Yeah, look at the pattern of the stuff we've done. So what do we equal this one to?
-2.
Okay, good job. -2. Now, what is the oxidation state of oxygen?
-2.
How
No,
many oxygens do you have?
you 7, so it'll be 14.
+14?
-14
Okay, so -14 plus what?
plus chromium, that'll be 2. So
2 what? Tell me what to write. 2x.
that'll be
2x, right? That's important that you guys
Yes.
see that. Since there's 2 of them, you got to put a 2x. And now you just solve for x. See that? So what is x?
Yes. X will be
+6. Okay, so that is how you find oxidation states for atoms if I give you problems, if I give you compounds. And this will help you in a reaction too, if you need to solve for somebody's oxidation state that you don't know. Okay, does everyone understand?
yes.
Okay, cool, good job, Austin. Now we actually start, okay, a reaction. Well, how do we apply all these rules to an actual reaction? Redox reactions, like Chloe said in the beginning of the class, are reactions that transfer electrons. How do you know? Because of that stuff that we were just doing, you'll see. That'll help you understand, oh, look, this guy's losing 2, this guy's gaining 2, so therefore, blah, 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 okay? There is a thing, there's an acronym that people usually use. There's 2 of them, oil rig or LEOGR. I like LEOGR because it's cute. And that's how it'll help you, those acronyms will help you remember which one goes with which one.
Isn't
Okay?
it oxidation is loss, reduction is gained?
I don't know, because that's oil rig. So I do Leo. Leo the lion goes grr, right? So Leo is, hold on, Leo is loss of electrons, means oxidation, means that I'm oxidized. And grr is the opposite. Gain of electrons means I'm reduced. Okay? So I like this one because it, I don't know, Leo the lion goes grr. It's cute. I don't like oil rig, number one, because I don't like oil mining. So I'm not going to use that one. But so yeah, Leo the lion goes grr. Okay, so that's how you know, okay, if this guy loses electrons, he's the atom that's actually getting oxidized. That's what oxidation means. Oxidation means if you have lost electrons. Okay, if you gain electrons, that means that you're being reduced. So that's how you would remember them.
Isn't it because if you're adding electrons, the number, like the negative number is increasing, but like that's like reducing. Like if you have negative $20, you have less than if you had negative $4.
Yes, you can apply that, but then that application really doesn't work with the oxidation name. The opposite doesn't work for the oxidation. But yes, it's sort of like that. It's sort of like that. You can think of it like that. But it's gonna be tricky because for those of you that really still haven't gotten the trick of electrons being negative, and if you have a negative charge, that means you're gaining, not losing. That's gonna be tricky for you guys. So this will hopefully help you. Remember, if I lose electrons, if I get more positive, yeah, I'm going to be oxidized. If I gain electrons, if I get more negative, I am going to be reduced, okay? So let's try that. Let's try that with a very simple redox reaction. Remember, redox tells you if it's a redox, it's because it's transferring electrons. The way that we know is by applying those rules to a reaction. So, can anybody tell me what the oxidation state of the magnesium would be here?
0.
0. Why 0?
Is by itself.
Because it is by itself and uncombined. Oh, you know what? I actually forgot to tell you when we were doing these rules. Okay, so your book actually fails to mention something, and I could be wrong, but I got this from your book. This slide is from your book, so when I got it, it didn't mention it, but maybe it does mention it now. So there's a extension to this free element thing, right? So yes, magnesium is 0. Good job, whoever said that. But an extension to that rule is if you have a free element, or if the element is in its most natural state and by itself as well. Okay, so for example, so do you understand what I mean? A free element like magnesium solid, or if an element is in its most natural state, if that's how you would find it naturally, which magnesium by itself would be found as a solid. For example, diatomic molecules, you remember those?
Chlorine gas would be
Yes.
0.
So if I were to go and find chlorine outside, would I find it by chlorine by itself? Or would I find it as a diatomic molecule?
Diatomic.
Right. So whenever you see something that is in its most natural state, right, and it's by itself, I mean, chlorine too is not by itself, but it's not combined to anybody else, right? So it's just a chlorine with a chlorine because that's how you find chlorine. Oxygen is the same thing. What's the other one? Broncliffe. So bromine is the same thing. Nitrogen is the same thing, right? So when you have things that are found that are by itself, quote unquote, and are in its most natural state, it would also get a 0. All right, so your book doesn't mention that, but that is part of the rule. So that's how you would know how to do this one, the O2, right? So magnesium is 0, correct. The oxidation state of oxygen gas, that's the way you would find it naturally in the world, would be also 0, okay? Everybody cool with that?
Mm-hmm.
You're gonna get a lot of those examples, so you will remember that, hopefully. Okay, now we have to assign the oxidation states of the products. What is the oxidation state of oxygen?
-2.
Right. You see how there's the number changes? Oxygen is 0 at the beginning, now it's -2. That means something is transferring. That means that this is a redox right there. That's what it tells you right off the bat. But what would be the oxidation state for magnesium then?
+2?
Right, +2. There you go.
And that's
Now,
because it's in the alkali.
sorry,
It's because it's in column 2, right?
I can't, sorry, you're breaking up, Chloe. What did you say?
It's because it's in column 2, right? Like one of the
Right.
rules was like,
Right.
okay.
Exactly. It's in column 2. And another reason is if you did the math problem, it would have to be -2. I mean, +2, right? Because oxygen is -2. But it's not a charge, it's a state, yada, yada, yada. Anyway, so, okay, now we can actually start figuring out, okay, who gets reduced, who gets oxidized. So what I do is I like to draw little lines. So magnesium goes to magnesium, and then oxygen goes to oxygen. Okay, magnesium, let's do magnesium first. It goes from
Reduce.
0 to +2. Is this guy losing electrons or is he gaining electrons?
Losing.
He's losing, right? He's getting more positive. So that's Leo. That means that this guy is being what?
Reduced.
Oxidized.
Leo. Leo. Loss of electrons means,
Oxidation.
right, you're being oxidized, right? So if you're losing electrons, which this guy is because he's getting more positive, he's being oxidized, yeah? So you would write Leo here, Leo. So that means that the other dude has to be the opposite, right? So the oxygen goes from 0 to -2. He's getting more negative. He's gaining electrons. So therefore, he is the guy who's he's the guy who's being what?
Gaining electrons.
Yes, but he's the guy who's being then
Reduced.
Reduce.
correct. That is how you find this. That is what those rules are for. So you would apply those rules to this, and that'll tell you who gets oxidized, who gets reduced. You're basically done, almost, with a redox reaction type problem, okay? So another thing, and I know Chloe had mentioned it at the beginning, is you have to know who is the reducing agent and who is the oxidizing agent. But it's easy because if you get to this part, then it's easy because it's always the opposite. So what do I mean by that? Leo is the guy that's getting oxidized. So he is the reducing agent. He's the guy that actually is doing the reducing because he's getting oxidized. Does that make sense? It's the opposite. So I would put reducing agent. And then the that guy is getting reduced. So what agent is he?
Oxidizing agent.
Right. He is the oxidizing agent. Exactly. So when I do these redox problems, I would do it in steps. So that way you don't have to wait, is he the Leo or is he the GER? I would do it in steps. I would balance the equation, obviously. I would then assign oxidation states. And then I would say, okay, who's the Leo, who's the GER? And then after assign who the agents, because it's always the opposite. You guys have concerns, questions? Because that's it. That's it. Silence. Okay.
We're processing.
Okay.
I think I have a question.
Okay.
Okay, so so how would you find the reduction? Why would magnesium be the reduction agent again?
He is the guy that is losing the electrons, right? If he's losing the electrons, he's giving electrons to somebody else. So he's reducing the other person.
Okay.
So that's why it's always the opposite.
Okay. Okay. Thank you.
Okay. So this is the first part of, well, the major part of doing a redox type problem is you got to know those rules. You got to apply them to everybody. And then you got to figure out who gets oxidized, who gets reduced. Okay. And then from that, you figure out what agent is who, right? So that's that. The second part of a redox type problem is doing half reactions. But I'm here to tell you, you've already done it. This, what you just did, like what we just did right there on the board, we've already figured out the half reactions. So it's just now actually writing them down. Half reactions are just, we're basically taking the oxidizing part and the reduction part and just, you know, writing them down. Say, okay, let me just show me just the oxidation, what's happening in the oxidation half, right? So who's getting oxidized? Magnesium, right? So magnesium's getting oxidized. I want to know, give me exactly what's happening to magnesium. So that would be the oxidation half reaction. And then let me show me exactly what's happening to the oxygen, the guy who's getting reduced. So I would do a reduction half reaction. The purpose of that, the purpose of that is to show how many total electrons are being transferred in this reaction. Because when you add those two half reactions up, you should get this, the reaction. Okay, so does at least the concept of half reactions, does that make sense? Hello?
Isn't it like saying what's happening in each step?
That's what I said, yeah. It's what's happening on each side, right? The reduction side and the oxidation side. So you actually just write down what's happening in the reduction, what's happening in the oxidation, and then you add them up. And when you add them up, you'll get this.
The whole reaction.
Right, right. So do you understand the concept of the half reactions? Because you do the half reactions after. And then you prove it to yourself that when you add them up, you get this. And that's how you know it's right.
And they happen at the same time though, right? The two half reactions happen at the exact same time. Because when one's like losing electrons, it's the other one's taking it, right?
Yes. So time-wise, this is one reaction. It's one reaction. So whenever you react it, the half reactions are not something that's happening separately. It's just you as a human being are writing down what's happening to one of the atoms. So it's not like it's a separate thing. It's just because as a human being, I want to write down so I can more analytically see what's going on to each element in this reaction. That's all. Does that make sense?
Yes.
Okay, so we have to have an oxidation half reaction and a reduction half reaction. So I usually do the oxidation one first, right? So again, you have the answer already because you've already told me who's getting oxidized. So what you do is you just look at, in the half reactions, you just focus on that person. So who's getting oxidized in this reaction?
Magnesium.
Right. So you would write it, and he's getting oxidized, right? So oxidized means that he's losing electrons, right? So the whole purpose of these half reactions is to show how many total electrons are being lost in this reaction. So if he's losing the electrons, I would write 2 mg, because that's what's on the left, right? Exactly what's on the left. 2 mg, arrow, right? Because the only thing that's happening here is that's it. I'm only focusing on magnesium because this is the oxidation half. So 2 magnesium, then at the end of the reaction, what is magnesium? What does magnesium look like at the end of the reaction?
Magnesium minus or plus.
Plus, finish your sentence.
Is it 2E minus?
Okay, so we're not talking about electrons just yet. Just give me what magnesium looks like on the other side.
It's got a 2+ charge, right?
It's an
Not a
ion.
charge, but
It's an ion, right? Yes, because it's an ionic compound. So therefore, it looks like this, Mg2+. You're not writing anything new here. The answer is right there, right? So it wasn't an ion before, right? Because it was by itself, it was a solid. But when the reaction happened, now at the end of it, now it's in an ionic compound. So therefore, the form that magnesium is in as the product is an ion, but you have two of them. So everything has to balance, right? So you would put a 2 there. Okay, this is the oxidation half. So the last part is now saying, okay, well, how many total electrons were transferred in this process? So you would put plus and then the total number of electrons. How many total electrons did magnesium solid lose?
2.
Each magnesium lost 2.
Oh, altogether.
Altogether, yes. How many did you say, sorry?
4.
4. Okay, so in this reaction, there is a total loss for magnesium of 4 electrons. Let's stop here and let you guys process. Do you understand what we just did? Because I mean, we didn't do anything. All we did is rewrite the oxidation half. And the only thing we added was, okay, so how many total electrons are being transferred here for magnesium? Well, how many total did he lose? He lost 4 because each magnesium solid was a 0. You have 2 of them, but then you got 2 magnesiums with a 2 plus charge. That means that 2 of them lost a total of 4. That's it. That's it. This is really it. Because then once we do the reduction half, then that is completely everything you need to know for a redox problem. Hello, you guys okay? Or no? Okay, so can someone else help me do the reduction half?
Yes.
Okay.
So, at the start of the reaction, the oxygen started off as a O2.
Okay, so first, before we start, this is the reduction half, right?
Right.
So the reduction half is the dude that gains or loses the electrons. Gains, right? So that means that the electrons have to be on what side of the reaction in this half reaction?
The left side.
It has to be on the left side. Remember, these are half reactions. So when you add them up, you're supposed to cancel these 4 electrons because you don't see that in this main reaction, right? So the same number that get lost have to be gained. So that way, when you add them up, they cancel. And you're left with the reaction. So do you understand that, Terion, or no? I asked you which side do the electrons have to be placed now, right? And this is the dude that's being reduced. So he's the dude that's gaining. So on what side of the reaction would the electrons now be, right? Because we have electrons here on the right side. So what side would this guy be on? The electrons, and I think Ariel said it would be on the left side. It's opposite. Do you understand? Okay, so tell me then what to write. Don't overthink it. Who's getting reduced? Oxygen, yeah? Yes, so tell me what to write.
Oxygen -2.
Wrong.
No.
Wrong. Because what is the form of oxygen on the left?
O2.
Okay, so it's not O2 with a -2. You understand that, right?
O2.
Okay, O2.
And then do the arrow.
No. You've got to gain, this is the reduction half. Gur, right? So you've got to gain electrons. The purpose of the half reactions is to show how many total electrons are lost or gained. So this reduction half has to show how many electrons are being gained. So how many total electrons are being gained by oxygen?
2 electrons.
No. Total, darling, total. Each oxygen goes from 0 to -2, each of them. But you have 2 oxygens. Didn't you tell me to put O2?
You did. Okay. Okay.
So then how many total electrons does oxygen gain?
4.
Correct. Yes. And you see it's the same number, right? Look at the oxidation half. Look at magnesium. It lost 4. So this dude has to gain 4. If not, it doesn't happen. It doesn't balance. It has to be exactly the same number. Okay? So now what do I do?
Now you put the arrow.
Yes, now I put the arrow. And now, what is the form of oxygen on the right?
O minus
I can't
2.
hear you, Karen. Sorry, go ahead.
O minus 2 or 2 minus.
Okay, so you just want me to write this, O2 minus?
Put a 2 in front of it. Put a 2 in front of it.
Thank you very much, because there's 2 of them, right? That is the correct reduction half reaction. That's it. So if you guys can do this, right, just realize what you're doing. All you're doing is, like Chloe said, you're breaking it apart. You're breaking up this main reaction into 2 parts so that when you add them together, look, this cancels and this cancels. So if you add 2Mg plus O2, so this guy, 2Mg plus this other reactant, O2, you get this ionic compound, which is this, MgO. Now I'm gonna erase all of this because I know we have to go so you can see it nice and neat, because this is a slide. Look, that's the oxidation half reaction, exactly what we did. This is the reduction half reaction, exactly what Terion said. And then if you add both of those up, if you add both of those half reactions up, look what you get. You get the reaction. So that's all we're doing, is we're splitting up the reaction so that we can then figure out how many total electrons are lost or gained, and then add it back up to get the reaction. It's like we're working in a circle. Okay? It is 12:02, and I know we have to go, but do you guys, and we're gonna talk about this again on Monday, obviously, because you guys are stressed out. I know, but that doesn't mean that you wait till Monday. You've got to practice this on your own. You have to do this. Know how to do these oxidation states off the top of your head, like really fast. Know how to figure out who's Leo, who's Ger, and then work on these half reactions. It's not hard. It's not hard. So I wanted to do more, but we don't have time. Do you guys have any general questions? Do you guys see how this is a lot harder than chapter 1 and 2? Yeah. Yeah, it takes a lot, it's a lot more content than 1 and 2. 1 and 2 was freaking sig figs and dimensional analysis. So imagine this exam. You're gonna have to do a lot. So that's why it's very important that you study. You study hard this weekend. Don't wait until Thursday. Okay, any questions? Okay, well, if you don't, you know, guys, it's 12:04. You don't look very happy, Terion.
I'm gonna get it down. This weekend is gonna be a very progressive.
Okay. So you have to, because it's next Friday, dude. So you got to.
Okay. I'm gonna come back Monday with like a whole professor.
What did you say?
I said I'm gonna come back Monday looking like a whole professor.
Looking nice, looking shiny, and with all kinds of great comments.
I have the knowledge floating over my head, literally.
Awesome. Can't wait. Prove it to me. All right. Let me know if you have any questions. You can email me, all right?
Yes, ma'am.
All right. See ya.
Have a good weekend.
Thank you, dear. You too. Hi, Destiny. Do you need something? Destiny? Hmm. This happened the last time.